Welcome to the video lectures for Module 6, in which we will treat Chapter 9 of the textbook on numerical integration. Here we see our chapter on numerical integration in a general overview of the course material. So we have already covered quite a number of topics so far. We've learned how to solve nonlinear equations or systems of linear equations. And in the previous video lecture, we discussed numerical differentiation. Today, we will elaborate on how to compute integrals numerically. Here you see the contents of the current lecture. And in the current lecture, the main question that we want to answer is this one over here. So we want to be able to compute for a general function f of x. We want to be able to compute the definite integral. So with a bound from x is equal to a to x is equal to b, we want to compute this definite integral of the function f of x. Now we start with a brief recap of the applications of integration, why numerical approximations are often necessary in integration, and we outline the basic approaches to numerical integration. After this, we discuss a number of integration methods. And these integration methods range from rectangle methods, midpoint methods, trapezoidal, etc. And a first class of such methods, what they actually do is they approximate this function f of x using a polynomial function defined on the interval from x is a to x is b. And we can distinguish these methods based on what kind of polynomial they use to approximate f of x. And for instance, if we use a 0th degree polynomial or a constant function, that leads us to rectangle and midpoint methods. If we use a first degree polynomial or a line, this will lead to trapezoidal methods. If we use a second or third degree, so a quadratic or a cubic polynomial, this will lead us to what's called Simpson's methods. Now I will also show you that further increasing the degree of such a polynomial does not always lead to a better approximation of this definite integral. And we will also look at a different approach in computing the integral, and that is through an approach called Gauss quadrature. And we will see that using this approach, we can really attain very accurate approximations of such an integral. As per usual, we also discuss the use of MATLAB built-in functions for numerical integration, so readily available functions that you can use out of the box. And I will discuss how to estimate the error that you're making using your numerical approximation of the integral, even if the exact value of the integral is not known. So whether we can say something about the error that we're making. That will be the closing part of this chapter.